We now cover an example which illustrates the formula we discussed in the previous lecture. So consider there is a wire. So this wire has mass m and it is suspended in mid-air. So under the wire there is a magnetic field which is holding the wire in position. The force acting downwards is mg, which is the force because of gravity, and the magnetic field is holding the wire in its position. So you know the formula for the force. So the force is equal to, this is the force exerted by the magnetic field. So this is the force exerted by the magnetic field. This is I times L vector cross product with the magnetic field. So this magnetic force has to be equal to the weight. So the magnetic force which is just acting in the upward direction, this has to be equal to the weight for the wire to be suspended, and that is what the condition we write here. So now you expand the cross product, you get ILB sine theta, where sine theta is the angle between the length vector and the magnetic field. Now the wire is lying on the screen and the magnetic field is going into the screen. So the angle between into the screen and lying on the screen, this angle is pi by 2. So instead of sine theta, you plug in sine pi by 2. So this is just 1. So the equilibrium condition for hanging is that the weight of the wire has to be equal to I times L times B, where again I is the current flowing in the wire, L is the length of the wire, and B is the magnetic field. So this is all given in the figure. Now we talk about motion of a charged particle in a uniform magnetic field. So say the charged particle has velocity v and it is moving in the magnetic field B. So case 1 is V and B are perpendicular. So in this case, the particle will move in a circle. The magnetic force, which will be q v vector times b vector, this will act as a centripetal force. Now let us see this in the figure or in the animation. So you see the particle is moving in a circle. So the force acting here is like this. This is the centripetal force. It is acting towards the center. The force is acting like this and the velocity is in this direction. Similarly, force is always acting towards the center. Force is always acting towards the center. Notice that the field is into the screen. So the field is into the screen, and therefore the force is perpendicular to always the velocity as well as the field. So because force is lying on the screen, it is perpendicular to the magnetic field and it is always perpendicular to the velocity. So this is the centripetal force right here. So this is the centripetal force mv square by r. So this centripetal force, this is equal to this magnetic force q times v vector cross product with b vector. So the magnitude here is qvb sine theta. But v lies on the screen and b is into the screen. So the angle between velocity and the magnetic field is pi by 2, because b is into the screen and v vector is lying on the screen. So this sine theta will become 1 because sine pi by 2 is 1. So you get qvb here. So centripetal force is equal to the magnetic force. So you solve for r and you get mv by qb. So you can cancel this out. Now if omega is the angular frequency, then the velocity is equal to omega times r. So this r is the radius of the circle in which the particle is moving. So that is radius of this circle. R is radius here. So instead of v, if you plug in omega r right here, you get r is equal to m times omega r divided by qb. So you do the cancellations out and you get omega is equal to qb by m. So that is the angular velocity or angular frequency. Now if the particle enters at an angle theta into the magnetic field, then the particle will move in a helix. So the perpendicular part will give the circular path and the parallel or the horizontal component will give us the motion towards the magnetic field. So let us see this. So you see the particle is moving in a helix. Now the particle enters the field at an angle theta. So the particle actually makes it makes an angle theta. So it has two components. It has a perpendicular component and it has a parallel component. So perpendicular you can say is a vertical component and the parallel component you can say is a horizontal component. But we talk about perpendicular and vertical component because we are talking about perpendicular and parallel with reference to the magnetic field. So for sake of simplicity, we have put magnetic field as the x-axis. So this perpendicular component, which is perpendicular to the magnetic field, this is the component which gives it a circular motion, just like in case 1. And the parallel part, the velocity which is parallel to the magnetic field, that moves it forward. So if a particle enters into the magnetic field at an angle theta, then the particle will move in a helix. If the particle enters perpendicular to the magnetic field, then particle moves in a circle.